Welcome to the second lecture of this course, Antenna Design by Writing Your Own Codes. Here you ask ChatGPT to help you get started. So as we also saw in the previous lecture, AI can convert your detailed explanation of the antenna design and build an HFSS model using scripting. And it has the potential to replace junior antenna engineers in near future. Any design, you put your words into a large language model, and then you get your input to HFSS, which is going to convert it into a proper model. Only those with a strong understanding of antennas will thrive. So theoretical knowledge is going to be necessary for advancing in your role. AI can help you gain that strong understanding. So it both presents a problem and then it presents a solution. You can write your own codes to simulate antennas and electromagnetic structures without having to master the programming tools at first. So how does this happen? We saw that in the previous lecture, but I presented this slide that you see on the screen using ChatGPT and the very well respected LaTeX compiler. So how did I do that? Let's get out of here. So I just want to emphasize that the key here is that you don't have to master these programming tools at first prior to getting started. So I want to probably emphasize this master the programming tools at first without having to master the programming tools at first. So how do I do that? So let's go. I can show you that I actually asked ChatGPT to write a LaTeX presentation with Beamer. The first slide is saying antenna design by writing your own codes, and all the rest that you see here I asked LaTeX to provide me with the code. So it did. I copied the code into a LaTeX compiler, which is this one as you see here, and then when you typeset it becomes this file. So let's go ask so here, without having to master I want the sentence without having to master the programming tools at first to appear in red. So all right, so it's rewriting the document. It's going to ask us to use some packages probably. So let's go to here. Some of the packages are already added, but we're going to do as it says. So the only thing that you can notice here is this text color has been added here, text color red, and then that sentence has been put in curly brackets. So this is how you learn that in LaTeX, if you want to change the color of something, this is the way you do it. So let's go ahead and do that. I guess I made a mistake also here as shown. All right. All right. So here's our first introduction to this course is completed at the second lecture. I hope you can subscribe to this channel so you don't miss our later videos. So by the end of this video, you will be able to run one simple command to do multiple things. What are you going to do is to run the C++ code that you have generated with the help of ChatGPT, compile it and then run it, and then there's another code that you have generated with the help of ChatGPT to simulate another problem. You're going to compile it and then run it, and then when you run it, both these files create some data file in the format of text. So some data files are created, and you're going to run some other codes in GnuPlot to create EPS figures for each of them, and then you are going to create some LaTeX documents again with the help of ChatGPT to summarize what we have done, and you're going to open up that document. It's going to be as simple as this. Run commands. All right. Your PDF file is generated summarizing what we have spoken about, some of the codes. I put them here, and the figures. I don't want to go into details of editing, so it suffices that we have been able to generate this file. And if you want to change something about your codes, you can simply go to the C++ files that you have created, and you modify your code, and when you simply run this batch file, it reruns your code, regenerates the data, and when you are done, when the computer is done, your plots are updated. So if you are interested in the antenna design theory and in computational stuff like this, please subscribe to this channel so you don't miss our next videos. So in the previous lecture, we were mainly at the theory part. We mainly focused on electrostatics. Today we're going to finish this, and we're going to move to also magnetostatics, and hopefully after that we will also show you how to write your own codes in ChatGPT, using ChatGPT to experiment some of the theories that we discuss here. So I guess in the previous lecture we came up to the point that we showed that divergence of electric field is your charge over epsilon 0, and curl of E is 0 everywhere. Remember, this is electrostatics, time invariant fields. So we know that if we know that also, as we used it, the identity that curl of gradient of any scalar function is going to be also 0. So we kind of use these two to say that, okay, then there is probably a field that is going to be something like this. E, if you consider these two parts, let's say, in order not to make a mess, so if you consider these two, so then probably we have E equals gradient of something that we call potential function. But then we also consider this negative sign here, as we saw in the previous lecture, that gradient of since it's going to be the gradient of 1 over r is going to be minus r3. So this basically negative sign will help us say that the potential function equals if it is for a charge distribution, it's going to be so that is our potential function. So this is going to be especially useful when we want to find out the electric field in scenarios where integrating over a vector component instead of this 1 over r that you have here, instead of this 1 over r that you have here, if you had r, it's vector divided by r cubed, so this would be more difficult to integrate. So using this potential function and then getting its gradient, it's going to be much easier to calculate E. So that's probably, like in most cases, that's the reason that this potential function becomes useful. So let's give you an example of a scenario where is probably a common occurrence. Say that somewhere in the space, if this is your x, this is your y, and this is your z, somewhere in space you have a positive charge and close to it there is a negative charge. Then you want to find out your field at an arbitrary point, say at P. So this is called a dipole, especially when this is positive Q. The charges are the same and their absolute values, they are negative of each other. So this is called a dipole. And yeah, this is like their position is arbitrary, but we could, without loss of generality, we could assume that they are actually located at the center of the coordinate system and along the along the z-axis. It turns out that when we solve that, it turns out that the result is such that it is not going to be dependent on its orientation. So let's go ahead. Okay. So this is x, this is y, and this is z. So I'm going to assume that I have my positive q at here and negative q at here. So these distances are d over 2, such that the whole distance between q plus q and minus q is basically d. And what I'm interested in is, say my observation point is here, somewhere here, and the distance between this point all right, so then there's also oops. So all right. So I have my three distances here. One is R1, one is R2, I call it, and the other one is R, and this angle is theta. So if I am to apply this integral here, basically it's going to reduce to just adding the potential of the individual charges plus minus q over 4 pi. This is R1 and this is going to be R2. All right, so I need to be able to do something here. As you see, for a triangle, that has one angle here, theta, and if this one is R, and if this one is R1, so what is the equation between R1, R, and d over 2? It can be written like this, that R1 squared is equal to R squared plus d over 2 squared minus 2r d over 2 cosine of theta. So that's the equation. All right, so then probably I can approximate this saying that, okay, R1 is now going to be equal to so what to do here? Well, let's keep it squared. So I'm going to take this R2 out. And then this becomes 1 plus d2 squared over R2 minus, now these twos are cancelled, so it becomes d over R cosine of theta. All right. So now, of course, this isn't going to be any helpful when this R is in the denominator. So I'm looking for some approximations here. And when I'm looking for some approximations, I'm going to make some assumptions. So what is the assumption? My assumption is that R, the distance, is much bigger than D. So this is important. Remember this. When this is the case, then basically D over R is much smaller than 1. And obviously D over R squared is going to be much smaller than D over R, and that is much smaller than 1. So I guess it is safe to say that then this kind of R1 squared reduces to R2 squared, well, almost equal to, approximately equal to 1. So I can safely basically get rid of this term here. So minus d over R cosine of theta. All right, that will do, I guess. And then, so R1 is going to be, of course, R all right. So then 1 over R1 is equal to 1 over R times 1 over, okay. So now we know that here this, you're using this all right. So then All right, then we can go back to the original potential function and write it as such that I'm going to these out, my 1 over r minus 1 over r2. And remember that when I have here, if I want to switch to the other R2 port, then if in that triangle for R2, what's going to happen is that this function, theta 2, if I call it, theta 2 is going to be equal to pi over 2 minus, pi minus theta. So cosine of pi, cosine of theta 2 will be equal to minus cosine of theta. Then your potential function will be 1 over 4 pi 4 pi epsilon r. So 1 minus minus 1. Now here, because of this is going to be plus cosine of theta, d over r, the whole thing to the power of half. All right. So now this is the point that actually, if you don't remember, you can actually use ChatGPT, ask ChatGPT to give you, this looks like something 1 plus x. So you can ask ChatGPT to give you the Taylor series for this. And the easiest way, of course, you're going to ask, like, what are the Taylor series expansion of, it's best to use this LaTeX notation, 1 over SQRT of 1 plus x. So if you ask it, then it's probably going to give you something in terms of that this is going to be approximated by 1 over 2x plus 1, 2, 3, 4, something like that, and then other series. So this is going to be negative. So from this, then you can estimate that this one is going to be, you can deduce that this one is going to be 1 plus half x minus where this is, and remember that what's going to happen here is that we don't care about x2 because x is already much smaller than 1, so x2 is going to be much smaller than x, and that is much smaller than 1 already. So then considering these will suffice. All right, so using these equations, this one and this one, so you can assume that x is always a positive number. All right, so in the case that is 1 minus x, so here x is d over r, so that's going to be 1 plus that. So let's say that then potential function is equal to q over 4 pi epsilon naught r 1 plus 1 over 2, and x was d over r cosine of theta. All right. So then the other part was there was a minus sign here. So minus whatever that is. And that is this one here, 1 plus d. So we are now using this equation, 1 minus 1 over 2 d over r cosine of theta. All right, so then potential is going to be q over 4 pi epsilon d r. So ones are going to cancel out and we have d over r all right. So what do we have here? So we have q d cosine of theta 4 pi epsilon naught r squared. That is actually the case. But remember that this comes with a condition. And that condition is what we stated at the beginning. Don't forget this ever. All right. Now, from here, one could look at this equation and say, what is cosine of theta? What is this? I mean, physically, what theta is what angle exactly? So coming back to this picture here, you can see that, well, d is simply this distance, right? All right, so d is simply this distance here. Let me show it with this arrow. And theta is the angle between that vector and actually this vector. Let me make this bold a little bit. All right. So theta, physically, so theta is the angle between the vector d and r. That's interesting. So now this basically doesn't depend on where your dipole is, and if r is the vector between dipole and observation point. Right. So then you can say that actually, okay, so we say that there is a vector called L, and that vector is basically the direction of the dipole, or to be precise, it's actually, I could show it as a unit vector. So that's in the direction of from minus q to plus q, right? So now my potential function can be rewritten as 1 over 4 pi epsilon naught r squared. I'm going to say p dot r. So r is going to be the unit vector of vector r, and p is going to be ql. sorry, QTL. All right, then this basically leads to Q is equal to potential is equal to QT cosine of theta over 4 pi epsilon naught r squared. The same as what we had before. So this is very important now equation, because although we started by a specific orientation of the potential, but now we have this function now. It is a more general term. So we could use this together with the superposition to say that, okay, now what if everywhere we have these dipole momentums? So if this pi, if this p, if this dipole momentum occupies a volume of dv, delta v, a very small delta v, then what I can say is that capital B is equal to divided by V. All right. So then obviously potential function from that is going to be P dot 4 pi r squared times delta V, right? This could be actually rewritten like this. The more familiar format we had, right, dV. Now if we have, now I'm going to say that because this is actually for a part of the bound charges, so the total would be an integral of that. That's going to be so we're going to have this equation. Again, another important equation. So obviously your electric field vector is now going to be gradient of your potential, and gradient is according to the free space coordinates, or and that's going to be equal to, this one here could be plus, if I change this, replace it with source coordinate systems. Okay, so now that's much better. All right, so let's continue like that. So now basically you have a vector in the integral. You have this vector dot product of gradient of some other, so then this will basically reduce to divergence of those two multiplied by those two. I mean this P over 4 pi epsilon naught and over R. This is P. Minus divergence of P itself. Right. That's what you get here. Okay. And then you apply the divergence theorem on the first term, and that becomes S prime P over R ds. Right. So I'm gonna minus all right. So I guess we are done with this potential function and its gradient to get the electric field for, these are called bound charges. And so from the looks of the equations, you can say that these represent surface charges, because the integral is over some surface, so it makes sense to draw that conclusion. And these are, of course, volume charges. All right, so then let's say what is my total electric field? That is going to be the field that is dependent on free charges plus what we had here, right? Or better say minus gradient of bound charges is going to be its surface charges, basically. R plus volume charges 4 pi epsilon. All right. So what we can learn from this, say I would like to obtain divergence of this total electric field. So this is going to go in this way, right? How this is going to go is this. So this divergence is going to be, for this one first, is going to be free charges by epsilon. It's going to be the case here. Now what we're going to say is that I want to be dealing with a function that, first of all, is not dependent on bound charges. I'm going to be dealing only with free charges. So how am I going to do that? So let's rewrite this one like this. Minus divergence of vector p, which is the dipole momentum. All right, so that makes sense. So now here that when we are taking the divergence of the electric field and and at that point it's important that we take this divergence here of the charge at the exactly same point. So then this operator will be equal to this operator. So whether you're using free space coordinate system or not, you're going to have the same thing. So if you want to write it down, so this is going to be plus so again, so if you want to bring it to the other side, plus P is going to be equal to the, so when you have this equation, so it kind of beckons to make this definition. All right. So this is why this equation is useful and why it is actually defined. All right. So now that we have this defined, we can proceed to say that curl of D, well, obviously, prior to that, we can easily see that actually divergence of D is going to be equal to rho, because that's what we had from the beginning, right? So we can proceed to write that curl of D is equal to curl of electric field plus curl of vector P. So we see that although this is always 0, but we don't know about this one. So what this means is that vector D, unlike E, may not be an irrotational field vector. But later we're going to see, or well, in most materials, it happens so that P is actually equal to some parameter is linearly dependent on E itself. So that means that this dielectric susceptibility is simply a constant, and it's going to that epsilon E so you're going to have again a constant number. So in this case where P is linearly dependent on E, so curl of D is going to be curl of D is going to be 0. So the force caused by a magnetic field, say B, on a moving charge that is moving with this speed vector is given by this equation where the Biot-Savart law provides how to calculate magnetic field caused by a current flow. So the face of this, the looks of it is very similar to what we had. R3, this is times. Okay, the only difference here is that this is a vector instead of the dot product that we had here. This is now a vector product. So I'm going to use some I am much in favor of the way Elliot in his antenna book is showing us the notation. So I'm going to bring this to the denominator and use this as mu 0 inverse. All right. So as before, we're going to be interested in knowing the divergence of B and the curl of B. So what these are. Let's start with divergence of B, which is going to be equal to, I'm going to take out that 1 over pi mu inversed and bring the divergence inside. And remember that this divergence is with respect to the free space coordinate system, J times R over R cube. All right. So now this is going to be the divergence of the vector product of two vectors is going to be equal to, well, let's keep everything together first. So this is going to be curl of J, so whatever that is, dot minus curl of R over R cube dot product J. All right, the whole thing dv. All right, so it's easy to see that this is now, because this is with respect to free space coordinate system, so this immediately reduces to 0, simply because it's just not dependent on that coordinate system. And then this part, curl of, we saw that r over 3 is equal to gradient of 1 over r, so we also know that curl of any gradient is identical to 0, so then this part also reduces to 0. So then we have divergence of B is equal to 0. So now we know. Proceeding, what we're going to be interested in is curl of B, which is going to be slightly well, more difficult to obtain, but we have to start from somewhere, right? Okay, let's say curl of B is going to equal to 1 over 4 pi, sorry, curl of J so let's back up a little bit and see that in vector calculus we had something like this. Curl of vector product of two vectors is going to be equal to this equation. Alright, so I know that these ones look a little bit weird, but we'll get to that and what it means in a few moments. So let's now focus on what these mean and how to expand that integral in the first place. So curl of B is going to be equal to 1 over 4 pi naught okay, how about I replace this with G, because there's going to be lots of terms, so it's simpler to just assume G is equal to R over R cube. All right, so then I'm going to be more looking to this J times G. All right, now let's start expanding that. This is going to be J divergence of G minus G divergence of J plus G dot nabla J minus J dot nabla G dV. Okay, now these are all vectors. Okay. All right, so without too much focusing on what this term means, it is somehow a derivative of it's going to be basically, I can write that in terms of, say that if J, if we were looking into this, this is going to be written as probably J dot gradient of GI, and then U. So UI is the unit vector of the ith component of that coordinate system, and GI is basically if G is given in terms of G1 U1 coordinate system, and in this coordinate system U1 U2 U3. So and yeah, so you see that because this gradient, now if J and G are reversed, so this gradient is with respect to the coordinate system of free space, so this is going to be reduced to 0. This is going to be reduced to 0. So what we have here from curl of B is basically, again, that constant over there, J divergence of G minus J right. All right. So what is divergence of G? Divergence of G is equal to divergence of, right, R over R3. And that one we already know that it's equal to, from previous lecture we have discussed this, and this is equal to the delta function. So so then this becomes a little bit simpler, and curl of B will be equal to 1 over 4 pi. So J delta okay. So now this simply reduces to, this term reduces to J, because the integral is going to happen only when we are going to get some value. Sorry, this reduces to only 4 pi J. So only when R is 0, and that's what we get. So curl of B here at this point is equal to J minus 4 pi 1 over 4 pi mu naught inversed J all right. So good stuff so far. And now I'm going to use what I talked about earlier here, this one. Except I'm going to make this, now this is with respect to free space, right? Or this is in general. So if I want to make that with respect to source coordinates, so then I'm going to have this. Sorry. J all right, that's interesting. Now you can rewrite curl of B being equal to J over mu naught inversed here plus 1 over 4 pi. Or not, I take this out. Sorry. Now this minus sign here with this minus sign here. So then I have a plus there. All right. So we're getting there, almost there. This is the divergence of the whole product, Gi times J. That's going to be now minus this integral Gi, divergence of dV. Okay. And now that's interesting because well, upon dV, I forgot that one there. So that one will be equal to, if you use the divergence theorem, so this can be equal to basically Gij ds, right? And if you, ds prime, if you consider this S large enough, there will be no currents, right? And so this term reduces to 0. And then it is interesting that divergence of JSJ, divergence with respect to coordinate system of J, is going to be equal to 0, because if this is not 0, this indicates that there is a flow of charge flowing out of some point. There is some point that is my charge source, and the charges there, if that divergence is 0, then the charges there are going to be a function of time. It's going to be time variant, and that's not the case here. So this term is also 0. So now curl of B simply reduces to this equation here. All right, now that we have established what curl of B is and what divergence of B is, which is 0, we can say that from here we can assume that there is a function A such that B is equal to curl of A. And the reason for that is that divergence of curl of any function is basically identical to 0. So there is a vector potential, vector magnetic potential such that its curl is equal to B. All right. So now what about the other parameter, the other equation, that curl of B is equal to J over mu 0 inversed. So we can say that, okay, now this is going to be equal to curl of A, and that's going to be equal to mu 0 J, or if you like Elliott's notations. All right. So about this, for any function, curl of A is equal to gradient of divergence of that function minus nabla squared A. And what is this parameter? It is basically well, it's nabla squared of AX, say, and then at AX or UX, or probably we were showing it, but just X plus nabla 2 of AY. All right. And we have already spoken about what this means. If you remember, we were talking about this function. Yeah. So divergence of curl of something is denoted by nabla 2. All right. So now that we know what it is, we can go back to writing curl of A is equal to gradient divergence of A minus this function equals. All right. So from here, we are free to say that, okay, we take this equation as a whole, but it would be easier for us if we chose a function A. When we are building A, we are choosing A such that its divergence is 0. We have its curl is B, but we don't have its divergence, so we say that we assume that its divergence is 0. So then this term reduces, and then the equation becomes nabla 2 of A is equal to minus J over epsilon naught squared. Now, this is Poisson's equation. Actually, this is a vector Poisson's equation. So in vector. All right. So from here, obviously, we have three scalar equations. You could write them down like this. All right. So we have all these equations. And then so now remember that we had this equation for phi for the vector potential of electric field. Right? And if we consider any of these scalar equations, and I'm so sorry, I made a mistake here. These are not vector, these are scalar functions. Right? All right. So if we compare any of these with this one, and then also considering that this led to the equation that considering this, so and the similarity between these equations, then one can easily write that, okay, if that's a solution for that function, then definitely this is going to be the solution for ax, ay, and az. And then we write similarly for ay and az, and then adding them up, you're going to have a is equal to all right. There we go. We have that equation as well. And all right, now that we have determined how to calculate the vector magnetic potential, then we can proceed to calculating the vector potential of a magnetic dipole of a current loop. And this loop is going to be or the radius of this loop is going to be much smaller than that of than the distance from the center of the loop to the observation point. So let's go ahead and have a look at that. So if I want to draw this loop such as all right, and the coordinate system is going to be probably something like this. X, Y, and Z. All right, and the observation point, let's say that it is somewhere somewhere here, let's say. And if I want to have the image of that observation point P on the XY plane, it's going to be probably somewhere here. All right, let's say somewhere here. And now these imaginary lines, probably I should draw them with a different color. So, all right, that should give enough precision for me. And we know that this angle, this angle is basically perpendicular. This line is perpendicular to the dashed line. All right, that's one thing. And let's say that we want to be focused on, start with a piece of current. Well, there's a current going around this loop, of course, and that is this current. All right, and we want to be focusing on a piece of current around here. All right, let's say that this angle is called phi. All right, and if I want to draw this line from center to the observation point, from the center, to the observation point, this angle is going to be theta. Now, this angle, I'm going to call it beta. All right. Now, if somewhere here also, if I consider some other piece of line here, that this also carries the same, of course, current. So if this angle is also beta, so we'll talk about that later. And of course, these angles are delta beta. Now, let's say that the distance from actually this point to here, I'm going to call that t. And again, it doesn't matter that it's a different line. It is also perpendicular to that line. So I guess we are all set here, except that this radius is a. I think I have everything I need to start our work here. Probably not. So let's call this distance r, and this one capital R, the dotted line. All right. All right, let's do something here. So we know that A is going to be dependent on J over R dV. Now in this case, this is going to be say I dl r, right? Now for every, if I want to focus on P, and there's going to be two current, like these blue ones that you see here, these blue delta currents at the two angles at phi plus delta and at phi minus phi plus beta and phi minus beta. So these two ones, right, these two ones, so those are going to be causing a field, a vector potential in the direction of phi angle, in the direction of phi angle at that phi. Now this direction, okay, is going to equal, so if I put them at this at exactly and of course this is assuming that the beta is much smaller than phi. I mentioned otherwise this is actually not a necessary condition. So if I want to write these or show these two vectors around this phi, if we look at this from above, again, if this is my center, one of them is going to be in this direction and the other one is going to be in this direction. So to me it seems obvious that this one, if I move this vector to here and if I move this other vector to here again, that's going to be something like this. All right. So now if we add them up here, they're going to be adding up in this direction. So these components will be canceling out each other. And the components that actually cancel out are basically based on sine of beta. So yeah, this angle is that angle is beta or pi 2 minus beta. This angle is beta. So if this is beta, and we know that this angle is beta, so what you're going to see is that minus I, well, dl times sine of beta plus I dl sine of beta here is 0, of course, in forming this integral here. So what we're going to be left with is this. If I want to simply focus on this component, that is basically, so the integral is going to be the integral is going to be twice the integral from 0 to pi, right? I dB cosine of beta. 4 pi. And why is dB cosine of d beta cosine of beta? And the reason for that is simply that this length if we go back to here, so that length, that dl is going to be equal to a, that is the radius, times d phi, right? So now if I simply want to make the integral based on beta, which is fine, it doesn't have to be based, so you can switch the parameters, it's going to stay the same. Right. So what are you going to have is that a is going to be equal to 2 times integral from 0 to pi. I'm sorry, there's an a missing here. AI cosine of beta over 4 pi mu 0 naught over r, and that. All right, here we see that we have a problem here, and that we from r, which is basically r minus r prime, so we can't make a switch here properly, and we need to do some calculations to find how how small r and capital R are related. So what we have from this picture, right, you can see that sorry, I would like to correct a mistake here, that this distance is obviously not r. It's going to be equal to, of course, r small r cosine of theta. And what I wanted to denote by r is, of course, by capital R is, of course, is the distance from the source to the observation point. This is r, and of course this t was initially the correct one. Okay, this is called t. Right, now it's going to make sense much better. All right, now so we have one t here, and this is the angle 90 degrees. All right, so we have then this equation for that triangle, which is going to be equal, which is going to say that R2 is equal to t squared plus r cosine theta squared. All right. And what is the value of t? So how to calculate t? Now if you consider for t, if you consider this triangle, I'm going to show it with green color. So this triangle will help you get, wow. Okay, so this triangle, right, will help you get the value of t. So this one here, this line here is going to be equal to r sine of theta. Of course, this line here is a, the radius, and the angle between them is beta. So then t is going to be equal to, t squared is going to be equal to r squared sine of theta squared plus a squared minus 2ar sine of theta cosine of beta. That's what we're going to have, and then using that up top for r, so if you use this t up above, then for r we're going to have r2 is equal to small r squared plus a squared minus 2ar sine of theta cosine of beta. All right, and then what is minus what is 1 over r, and that's going to be 1 over 1 so if I move this term to the end, it's going to be 1 minus 2 2a sine of theta cosine of beta r, then plus a over r2. So this is much smaller. So then this is going to look like that this term is also much smaller if this is x. So this is going to look like 1 minus x. In Taylor series we have seen before what this means. So this is going to be approximated by 1 x, and so this one will be almost equal to 1 over r, 1 plus a sine of theta cosine of beta over r. All right. So now back to this integral here. So if I want to rewrite that, I can, I can write a is equal to 2 times integral from 0 to pi ai cosine of beta over 4 pi mu 0 inversed and over r one plus a sine of theta cosine of beta over r d beta. So now this is going to reduce to, I take the constants out, sine of theta and the reason that I can do like this is that simply the cosine function, if this is multiplied by 1, its integral is going to be minus sine, its integral is going to be sinus, and that is simply from minus sine of pi is 0, and sine of 0 is also 0, so that integral will be 0, so we won't be bothering with that. And so what's going to be remained is here simply this term. So taking out the constants out, I will be having this one here, and if you compute that one, then this will be pi over 2 equals I squared, I times a squared 4 pi so again, like, I have this formula, right? But oh, I must have missed something here. The vector sign got lost somewhere. So going back up, I want to see where I lost my vector sign. So dl right. So this is so I'm not sure, this is probably in the direction of phi. That's for the observation point, right? And this looks very much like if I add pi here. Oh, this didn't have pi, so 4 pi's are cancelled. But if I put the pi's back on, so what you see here is this pi times a2 is basically the surface. So it becomes like pi a2 and times I times sine of theta, and then what's in the denominator is 4 pi mu 0. Oh, all right, so that's nice. And then the point is, now I can say that this is the surface, the area of the loop, and this is the current of the loop, of course, and this angle theta is the angle between the observation point and the line that is perpendicular to the surface of the loop. So if this is my current loop, so that angle. Right? So yeah. then I define M as S I vector S, and then R is simply the position vector, the vector from source to observation point. All right. So then A can be rewritten as M times R over 4 pi all right. Double check and see that this will give us the correct direction actually. So in our example here, M, the direction of M is Z, and R, if the distance is large enough, then it's going to be R direction. So say Z times R. So that's that seems to be right, and it gives us the phi direction. All right, so I write into ChatGPT that the electric potential function of a dipole is given by QD times cosine of theta over 4 pi epsilon r squared in spherical coordinate system. Determine the electric field by computing the gradient of the potential function. Of course, I made a mistake here. I forgot to mention the negative sign. So, but what it does, it actually includes that negative sign, which is interesting. It so gives you the formula for gradient, and actually computes that. So with respect to R, it takes the derivative okay, and with respect to theta, it also calculates it quite so with respect to theta, yes, that's also accurate. With respect to theta, QD 4R epsilon, okay, and with respect to phi, it's 0. So then it gives you this gradient V, and the electric field is negative of that. So things seem okay. And then I say assume that D is, so my intention is here is to plot it against, in terms of D. So, but I don't want to go into the details of doing that, so it's easier to assume that D is equal to 1, Q is equal to 1. So then when I plotted versus R, basically it's going to be in terms of R over D. Write a C++ code to compute both theta and R components of the electric fields for different values of R, ranging from save the results into a text file. The first column in the file is the R values, the second column is the theta component, and the third component is R component. All right. So it gives us the code. It's interesting. Here it says out file well, obviously it's opening the file. It's putting it into this file called electric_field.txt. And all right. So what's interesting here is that it actually picks a theta pi over 4, which is very interesting. It picks it an angle where both of them are going to be almost the same sine of pi over phi and cosine of pi over phi. So it picks a very interesting value for that, and basically does that comparison. Right. Let's now copy and paste this into something that we can run by C++, let's say. All right. So I will call it Vim. I use this Vim text editor, which is probably the best one. I don't recommend that you guys use it, but it has a very steep learning curve. The good thing about this Vim is that you don't have to use a mouse. It has visual modes, and it has insert modes that basically for navigating around the document you only use your keyboard. In the visual mode, when you press a keyboard, when you press a key on your keyboard, it doesn't insert text, but those are just ways of getting around. So let's call this lecture 2, and we'll call it the first code, first CPP. All right. Now this, I have a plugin for CPP, that's why. So I copy the code there, I get out, write it, get out of there, then G++. Actually, where am I? All right. So G++ lecture 2. Let's run that file. All right. Just to make sure if I have already file called electric_field.txt, I'm going to delete that electric_field.txt, right? Yeah. So I'm going to delete that probably before. So I'm going to run that file. All right. Now let's look at the file electric_field.txt. All right. So as we expected, so values of R are running from 0.1 all the way to, yeah, and the first column, second column, and third column are there. So now I need a way to plot those, and of course GnuPlot is, in my opinion, is the best way to do that. Of course, later when you are dealing with large amounts of data, probably GnuPlot is easy to deal with large amounts of data to plot. Write a code in GnuPlot to open the text file and plot the two components, the two field components, that is columns 2 and 3 based on the first column. All right, so it gives me this code that now it's interesting that it sets terminal to PNG. So the output is going to be a PNG, electric fields.png. So I want to basically remove this file. If I have it before, all right, it's removed. So I'm going to open and plot fields.gp. So okay, let's copy this code into plot fields.gp. Oh, that's the name it recommends. All right. Now The way you run that file is called GnuPlot plot.fields.gp. Alright, so now you're supposed to have that file, that PNG file. It's supposed to be generated. ls. Alright, let's see if I can open it with electric fields.png. Okay, I said that it doesn't exist because I missed S in the beginning. Alright, so if you look at this section here, you see that there's something here and then I don't have anything at the rest of the plot. It's just because for small values of R, this field is so huge that the smaller values are basically simply not visible. So there are ways to do this. So one way is to use the logarithm of that, but I don't want to get into that. So I want to do something else. I want to choose so let's change a terminal to PDF. So the file that opens is a PDF and I can easily zoom. Okay, so the difference is that now if I copy code, if I open the same file here, okay, now see, I'm in the visual mode. I select everything, delete, insert mode, paste. Now the terminal is PDF. It's creating a PDF file when I run this code. So calling GnuPlot again. Now a PDF file is going to be created. So instead of this PNG, I will write PDF. Let's see what happens. All right, yeah. So a PDF file is created. Now I can zoom in and not lose my data. I see that I have two plots here, right? And yeah, for ER and E theta. All right, but still there's a problem that I can't see them properly. So what I say is that change the GnuPlot code to start using the data from the 5th row. So hoping that this is going to basically ignore those very large, very small values of R and such very and thus ignore the very large values of E. So the plot is going to be okay. So copy this, go to that again. Notice the difference that it says skip 4 with line, so it's going to skip the 4 rows on top. Okay, GnuPlot. All right, let's open the file now again. Well, it doesn't go to some values of 10 to the power of 12, but it's still, it's too large. It's nothing that I could use. So let's do something like this. Let's say that to plot the data, change the GnuPlot file to only plot from 10th row to the 100th row. Okay, let's. All right, so this is much better now. So what you see is that we are starting at almost our R is equal to 1, smaller, a little bit smaller than 1. That means that R is almost equal to D. And the electric field is calculated, and we see that, of course, E theta is almost double of what ER is. And so that concludes this section, but probably this plot is good to have. So notice that I'm not bothering with the units, the x-axis labels, y-axis labels. So let's make one final request to ChatGPT and say that change the terminal to EPS enhanced. Okay, so PostScript EPS enhanced. So we're going to see that the EPS file that is being generated, we're going to use it later for something else. And so let's say that I want to go into this Vim, and again say that I want to delete 10 lines, and now 4 lines I want to delete. Okay, now paste everything, call GnuPlot, ls all right, finally, yeah, that's right. Okay, so now we have our EPS file as well. Now we can actually go to what we talked about earlier to okay, so we input our entry into this is to basically compare the electric field that is directly computed by adding the 2 electric fields of the 2 charges versus the electric field that is computed by the potential function that we calculated, but then by calculating the negative of gradient of that. So one, determine E, which is electric field, and is equal to negative of that the potential function. And second, so assume that theta is equal to pi over 2, some values for that, and then calculate that for some range of R, and then in the same C++ code compute ET. So we come over here and we see that it's doing pretty good job of doing that calculations here, getting the E theta component, and especially I tell him that it's the E theta component that I'm interested in. And there's one problem here, that when it's writing the code, so I have only 2 R's here. So for that E theta, I should have 1 over. So it's over R 1 over R to the power of 3, but I have only 2 R's here. So it's important to pay attention to the code, because ChatGPT is going to make mistakes. So what I'm going to do here is, let's see what I have. Okay, so Vim lecture 2. I'm going to go second code, second CPP. Okay, come down. All right, so I said that I have to change that to compute that this is for r over 3. Okay. Not r over 3, sorry, 1 over r to the power of 3. So let's do that. All right. And what's the name of the file that is creating? It's called output.txt here. Okay. So it's, sorry. Output.txt, no such file, so that's great. So then let's say G++ lecture 2 second CPP. Let's run that. Excellent. So now let's look at that. All right. So we just compiled the file and we didn't run it. So let's run it. And ls output. Yeah, there it is. Output.txt. All right. Now let's ask this. Write a program, write a GnuPlot file to use the above mentioned output.txt file and plot the E theta, plot E theta and ET versus R. Okay, it's again setting the terminal to okay. So it looks like there is some issue with plotting it in the PDF terminal. So let's not dwell on that one. And so we see that the two values give us pretty good approximations, which is basically, to be honest, is not what I expected, since we did use and all right, so I changed the x-axis to the linear values instead of, well, I forgot to change the label, so let's go change the label. Okay. Plot. So as you see, these two approximations are different from each other. These two approximations are different from each other. Well, actually, the approximation that E theta, so I forgot which one was actually the approximation. ET is probably, yeah, ET is probably the accurate one, and E theta is the approximation, yeah. And we see that they are different from each other for small values of r. And the reason for that is basically what we had discussed before, and it's that that approximation is only valid for is going to be valid when r is greater than d. And to be honest, here we see that they have values that are much close to each other, that actually I'm surprised that they show they give us similar values for 0.5 and 0.6, but this is perhaps because we're looking at only one component. One component of the electric field, and that is E theta. So now I want to change the code to, well, modify the GnuPlot code to change the terminal into EPS enhanced, and to use linear values instead of logarithmic ones. So let's copy this code and so that is going to be plot EPS. All right, GnuPlot. Let's run that file. All right, so let me see how many EPS files I have. Okay, 2. There is electric underscore fields and plot.eps. So I'm going to ask ChatGPT now, write a LaTeX document containing all the details of this conversation, and to use and to create 2 figures which use the files electric fields EPS and plot.eps. So the document that this has created, it doesn't automatically put every single detail. It says that the C++ code from conversation is placed here. Of course, you can do that yourself, but then let's go ahead and create the document. Let's say document.tech. That's the name that it recommends. So I'm going to place everything here. And it says right, a PDF latex.document.tech. So, all right, and you usually run any LaTeX command twice for referencing reasons, and say open document PDF. Okay, let's place the Nice. All right. Okay, now let's continue with this. Let's do some plotting. So let's say that what was the file responsible for creating the first plot, lsgp. So the name of the file was plot fields. Plot fields. All right, so it seems like the commands that we want to run is this one, g++ lecture 2 underscore first. So okay, so now I want to write a program that does this automatically. Now write a batch file for Mac which runs the following commands. So first one is g++. Okay, first this one, second third, four, 5. Now that the data are created, now we're going to have to use these GnuPlot commands. So we're going to call GnuPlot to create those, GnuPlot to run this command, and 6. This GnuPlot. So now my EPS files are created. So, and that LaTeX file, I already have it there. So I can go back and run this file again. PDF LaTeX command, I can go and run that again. Where is that? PDF LaTeX. Okay. Can go that, run that again. 7, 8, remember I have to run it twice. 9, open document.pdf. So let's see. Okay, it's interesting that it refuses to use my simplistic version of A.A, and it just creates objects and runs those. So let's see. Copy this VIM and so let's name it run commands sh, run commands sh, and then it's telling me to run this. Oh, okay. It's asking me to do this and then run the previous one. What was that? Okay. Okay, this is the GnuPlots probably. Okay, now it's asking that the plot EPS does not exist. Probably plot EPS does not exist, and why is that? Okay, so it looks like I'm running the wrong version of the file. I have to put underscore here. Okay, now let's run that again. Let's run that again. Okay. All right. So now those are created. Those are placed here. So let's place the C++ code in the LaTeX document. So where is the C++ code? So I'm going to place only this one, the ones that's more interesting. Contains the so let's go back to our terminal here, Vim document tech. So the something. Oh, that's not right. Okay, I'm not going to write that. Okay. So you put that code over there, and now let's see if this is actually going to compile properly. Let's see if the LaTeX file is going to run. Okay, it seems like everything went ahead just okay. So this is adding some formatting to the code as well. Now it says GnuPlot code goes there. Let's go to the GnuPlot code. The last one that we had before the LaTeX document, GnuPlot code is here. Let's copy this and go again to the Vim document, and GnuPlot from is placed here. All right, let's copy that. Okay, now let's run the document again. Run the whole thing again. Now remember that this is running the data. This is, imagine that you are dealing with large amounts of data, and you have made a mistake in your code. And so if you want to go to your code and change your code, your data will be changed. So you have to plot them again. You have to now insert those. If you were using regular, say, Word document, and the regular processes that everybody, like most people use, so at this stage you would have to go run your codes again, generate your data again, and just use your plotting function, whatever you were using, plot them again, and then import those files, import those plots in your Word document again. So this is a little bit tedious, and especially if you have to constantly change something, if you are in the process of trial and error, and if you want to make sure that you are not you won't have to do everything. You won't have to do everything all the time. You won't have to repeat the simple things every time. And if you want to make sure that you won't have to repeat the same steps every time, so this creating bash file is the way to go. For example, now we had these CPP files that we had called in our file. Say that one of them we want to make a change, lecture 2 second, we want to make a change to that, some change that you're going to have to probably, now I am going to make a mistake here and say that, okay, now what I want to compare is that actually say for some reason my ET was actually 12, right? So you don't have to do anything, recreate the plots, put them manually in your document and create a PDF after that. You don't have to do that. You simply run this, right? And then it creates the plots and puts them in your document again. So the values have now changed. So I'm going to it's in this one that the values have changed. If you see E theta is coming up to 8 times, is coming close to, is between 8 and 10 times 10 to the 12. So let's say that I have realized that I have made a mistake, and I go back to the file that where I made a mistake. I change it back to what it was before. All right, and I simply run that batch file, and I get the correct results. So from our next video, we will enter the field of electromagnetics, and from then on we will talk about only antenna matters. So please subscribe to the channel so you don't miss out our next videos. Thank you.